Today, we're gonna unravel a fascinating story. It's about a dangerous parasite that meets its match. But not in some fancy new drug. Nope. It meets its match in a mathematical equation. This is a real-world detective story for vets and public health, so let's get right into it.
Oh, and just a quick heads up before we dive in, if you find this breakdown valuable, hitting that subscribe button and leaving a comment really does help us create more content just like this. We appreciate the support.
All right, every good story needs a villain, right? Well, the villain of our story is microscopic, but it has an absolutely devastatingly effective strategy for survival. We're talking about a disease called cystic echinococcus, or CE for short. At its core, it's a parasitic disease caused by tapeworm eggs, and it's a huge problem. It doesn't just threaten the health of farmers and their animals, it can actually cripple local economies and lead to real poverty. So how does this nasty parasite keep itself going? Well, it's all about this life cycle. It starts with an infected dog, which releases parasite eggs into the environment through its feces. Then, an animal like a sheep comes along and accidentally eats those eggs while it's grazing. Inside the sheep, these eggs develop into cysts in its organs. And here's the crucial final step. When that sheep dies, if a dog eats or is fed those infected organs, the dog gets infected, and the whole vicious cycle starts all over again. Humans, by the way, can get caught in this loop by accident too. So, this brings us to the million-dollar question. To stop this disease, we have to break that chain. But with all these moving parts, you've got dogs, sheep, the environment itself, where do you even start? What's the weakest link?
The answer, and this is the cool part, comes from a field you probably wouldn't expect to be on the front lines of veterinarian medicine. And that field is mathematics. Think of a mathematical model as a kind of digital laboratory. Instead of running expensive, time-consuming experiments in the real world, scientists can build a complete simulation of the epidemic. This lets them test all kinds of different control strategies, vaccines, health campaigns, you name it, to see what actually works best, all from the safety of a computer. So, how exactly did these researchers build their digital laboratory for this particular parasite? Let's take a look under the hood. They use something called a compartmental model. It sounds technical, but the idea is simple. They just sort everyone and everything involved into different groups, or compartments. So you've got your healthy dogs, your infected dogs, your healthy sheep, your infected sheep, even a compartment for the parasite eggs just hanging out in the environment. It creates this incredibly detailed map of how the disease moves.
Now, once that digital lab is built, the researchers can start hunting for the key that unlocks the whole mystery, a single, incredibly powerful number. And that number is the basic reproduction number, or R0. You've probably heard this term before. In epidemiology, it's the magic number. It tells you, on average, how many new infections a single case is going to cause. It's basically a measure of how contagious a disease is. The rule of R0 is dead simple. If it's greater than 1, each sick person or animal creates more than one new case, and the epidemic grows. If it's less than 1, the disease can't replace itself, and it just fizzles out and disappears. The entire goal of public health for any disease is to shove R0 below 1. So, what did the model find for this disease in the Ningxia region of China? An R0 of 1.0056. I mean, look at that. It's just barely over 1. But that's enough. That tiny little bit over 1 means the disease is self-sustaining. It's persistent. It's not going away on its own. Now we know the problem, let's find the solution. Okay, so now that the model's built, we can start playing with it. We can use it to figure out which specific action will have the biggest impact on getting that R0 number down. And I gotta tell you, the answer might not be what you think. So think about the two most common strategies, right? Deworming the dogs and vaccinating the sheep. They're both super important, no doubt. But the model lets researchers ask a much more precise question. Which single action gives us the most bang for our buck when it comes to lowering R0? And here it is. This is the big reveal. This chart shows us which factor lowers R0 the most. And yeah, you can see that deworming and vaccination, they both help. But look at that third bar. The intervention with the single biggest effect is carcass and viscera management. In plain English, that means properly burying infected livestock and, crucially, not feeding their organs to dogs. The authors of the study put it perfectly themselves.
They found that just emphasizing how to manage infected livestock during health education has the potential to significantly reduce the risk of transmission. That's it. That's the weakest link in the whole chain.
This is fantastic news, right? Because it means we can take these mathematical insights and turn them into a concrete, practical plan of action, especially for veterinarians who are out there on the ground. So here's what that looks like in the real world. This table translates the model's geeky parameters into simple advice. The parameter Q becomes a simple rule. Teach owners to never feed raw organs to their dogs. The parameter B becomes clear guidance. Tell farmers to bury or burn infected carcasses. Now, this doesn't replace deworming or vaccination. It just supercharges their effect by hitting the most critical point of transmission. So here's the most important takeaway. The medicines, the vaccines, they are absolutely vital pieces of the puzzle. But what this model proves is that the most powerful weapon we have in this fight is actually just knowledge. Simple, low-cost changes in behavior, driven by targeted education, can break the entire cycle. And that leaves us with one final thought. We're talking about a complex, multi-species parasitic disease, and it turns out the most effective solution is a simple change in habit. It really makes you wonder, doesn't it? What other huge, complex problems out there could be solved if we just found the right, simple behavior to change? Hey, if this explainer helped you understand this topic a little better, please consider supporting our work. There's a link to our Buy Me a Coffee page in the description. It really allows us to keep breaking down complex research like this. Thanks for watching.